The second of the biomechanics videos looks at Sir Isaac Newton and his 3 laws of motion. And from the specification, you need to be able to apply the 3 laws to a variety of sports techniques. So we'll go through a couple here, and you can obviously do some more in lessons. Well, Newton's first law is the law of inertia. So what does inertia actually mean? It's the reluctance to change of an object. So what's key is it could be that you're talking about a stationary object, or you could be talking about a moving object like a ball. And basically those bodies will not particularly want to change motion unless a force or something else affects it. So let's look at the definition. Every body at rest or moving with constant velocity in a straight line will continue in that state unless acted upon by an external force exerted upon it. So a ball sat on a tee there is quite happy sitting on a tee there. It's got no desire to change motion. It is reluctant to change. It doesn't want to change unless an external force is exerted on it. So unless it's whacked by a golf club. The ball, if it were rolling along the green, is quite happy rolling along the green and won't particularly want to change its motion unless an external force is exerted upon it. Now, actually, that external force might be friction, if based on it rolling over grass, which will eventually change its motion. So if you were ever in a situation where there was no friction, this moving object would happily continue in its constant velocity, in its constant direction, unless an external force is acting upon it. Unless, if you think about an ice puck travelling across the ice, it will just carry on until it hits the side of the rink. So inertia refers to a body's reluctance to change, but it's whether it's stationary or moving, it doesn't matter. It will only change its motion if inertia is overcome, and that means something else, some external force acts upon it. So this golfing example here is a good example of showing inertia in a resting object. I think I explained it earlier. The ball will remain there, not moving, until an external force is acting upon it. So here's an example of a moving object. So whilst running, this athlete has a certain force acting against her. So let's say wind resistance is trying to change that motion. However, the force that she is generating through her pushing on the ground is equal to that force. And what that means is there is a zero net force. The force trying to slow her is equal to the force she is producing moving her forward. And what this means is there is a constant velocity, so she is running at exactly the same speed. There is no unbalanced external force here, and therefore there's no change in motion. So the forces in those 2 directions, one forward and one backwards, are equal, cancelling each other out, which means that motion is constant. So, moving on to Newton's second law of motion, and this is the law of acceleration. And here's the definition. So, the acceleration of a body is proportional to the force causing it, and the acceleration takes place in the direction in which the force acts. So, I hope you can recognise here there are 2 parts to this definition. One suggesting that the acceleration you have is proportional to the size of the force you apply. So if you apply a small force, the object will accelerate or have a small acceleration. If you apply a larger force, then there will be a proportionally larger acceleration. So this shot putter, if he exerted a small force, there would be small acceleration, and a larger force would generate larger acceleration and probably a larger throw. Similarly, the direction, or in this case perhaps the angle with which the force is exerted, will determine acceleration also. So the performer might project the ball at this angle, in which case the shot put would take this parabola, this route. Or they might change the angle and project it in a different direction, in which case it takes another route, or this angle takes another route. So in terms of the law of acceleration, it's the size of the force that matters and the direction of the force that ultimately determine acceleration. Here's going back to our running example. So in Newton's first law, we looked at constant velocity, where there was a match between the resisting force and the propulsion force, the forward force that the athlete had. Now looking at this picture, we've got a resistant force there, perhaps by wind resistance or air resistance, but looking at the angle of this athlete's body, you can see that where they're contacting the ground, they're actually also creating a backward force. So we've got a resistant backward force, and the athlete is adding to that backward force. And that would kind of suggest that this is perhaps near the end of the race, or when they're fatiguing and they're actually slowing down. So in this case, there's not a balanced force, there's an unbalanced force. Both arrows are backward forces, and there is a net backward force, which means that she's basically slowing down. Now, if I add a larger propulsion force or a forward force, what we've got here is a slightly different version. So we've got our resistant backward force, our air resistance, being applied on the athlete trying to slow her. However, because she is generating a larger forward force, this is again a net force. There is a bias force, and in this case that would bring about acceleration or horizontal acceleration. So she would be driving forward and speeding up running, and that might occur earlier in the event or as she's moving out of the block. So either way, if a net force is present, i.e. there's a dominant force that way or a dominant force that way, we've got a change in motion. We've got acceleration or deceleration. And what this shows is a relationship between force, mass and acceleration. In fact, mass is quite an important one, which I'm sure again applies to many of your sports. So if we look at this example, here we've got two fine athletes. Now, if this was a 100-meter sprint and these guys were in the starting blocks, and we know that they applied exactly the same force against the starting blocks, who do you think would accelerate at a greatest rate, and why? So have a little think. Well, I hope you put that this thinner or lower massed athlete would. So if they applied the same force, because they're a smaller mass, they will be able to accelerate at a greater rate. This larger massed athlete applying the same force would only accelerate at a smaller rate, or be slower out of the blocks. So what we know here is that the greater mass there is, the greater the force we need to generate acceleration. So if this larger athlete wanted to win, he would have to generate much bigger forces in the blocks to get him to accelerate at the same rate, to keep him head to head with this smaller massed athlete. So I guess mass can be an advantage or a disadvantage in performance. In this case, this sprinting example, it might be a disadvantage because they've got to work harder to win. If you're a rugby player and you have a large mass and you're sprinting towards the try line, the defender would have to generate a large amount of force to decelerate you, to slow you down or to stop you. So in that instance, having a larger mass might be an advantage, because if you were smaller, they might be able to tackle you more easily. They wouldn't have to create as big a force to decelerate you or slow you. So mass will matter in terms of acceleration and deceleration. So the greater the mass is the less acceleration if the same force is applied, just to go back to that example. So finally, Newton's third law of motion. This is the law of action and reaction. And a way perhaps of remembering this is there are 3 words associated with this sort of title of the law. So to every action there is an equal and opposite reaction, a reactive force. So for every force that is applied, there is a reactive force that applies back onto the object. And the sprinter here is a really simple and perhaps the easiest example. So in order to drive out of the blocks, this athlete is generating a force through their muscular contractions to push via their blade back against the block. But the block will push an equal and opposing reaction force or reactive force back onto the athlete, and in this case, because the block is fixed onto the ground and the ground is basically the earth, the planet, we're not going to push that, so this becomes immovable. And what that means is this reactive force that pushes back on the athlete, who is relatively small, will cause them to accelerate and drive forward. So they push back on the ground, and the ground reactive force pushes them forward and out. If you were to jump in the air, you push down on the ground and the ground pushes you up into the air. It's exactly the same concept, but it's an equal and opposing reactive force. There's the force on the ground, and there's the force pushing back equally and in opposition. So here's a couple more examples. Whether it's the leg kick action generating a backward force, or whether it's the arm pull action pushing water backwards, there is the water pushing you forwards. That's the reactive force. Or the diving board. The swimmer here pushes back on the diving board, and the diving board pushes them forward. Or the goalkeeper pushes on the ground at a certain angle to dive, and then the reactive force from the ground pushes them back at an equal and opposing angle to match that. So, Newton's 3 laws. This is perhaps a way that might help you remember which is which. So I've put the I in blue. So inertia is the first law, and I think that the I looks like a 1, so it's the first law, inertia. Acceleration has 2 C's, and also there are 2 parts to it. If you remember, it was about the size of force and the direction of force. So the second law has 2 C's and 2 parts. And the third law, as I just said, has 3 words, action and reaction. So first law of inertia, second law of acceleration, third law, action and reaction.